I want to talk about concatenation of a cubic structure. Here's a motivating question from number theory. So suppose we're given a collection, a system of k polynomials and r variables with integer coefficients p1 through pk, and we want to ask the question: can we have all the progressions, so polynomial progressions, x plus p1 of m through x plus pk of m, simultaneously prime, and if so, how often? Okay, so there are various conjectures about polynomials and real configurations and primes, and so I wrote some names that some of them are more general in this, and some of them are less general. But basically say that you can have x plus pi of m be prime infinitely often if and only if there are no local obstructions. So what does that mean? So what is no local obstructions is some trivial divisibility condition. So, well, if we want this thing to happen, x plus pi of m all to be prime, then we need to know that for any prime p, if we have some choice of x and m1 through mk and 1 through mr, so that all these expressions, x plus pi of m,
not divisible by p. This doesn't happen, then obviously we can't expect them all to be prime. So this is the no local obstructions, and also these conjectures also conjecture asymptotics for the number of. So in some box, you take m in some range and x in some range, and you ask the asymptotics in some range. Okay, so in a series of papers of Green Tao, and last one by Green Tao and myself, we prove this conjecture in the case when all degrees of all polynomials are smaller or equal than 1, and the degrees of pi minus pj are all exactly 1. So that rules out the case of x plus 2 that we would really want to say something about, but covers all cases other than that. Okay, maybe. And also, so we show this, and we also obtain asymptotics for this. So the number, we can count the number of x and mi if all are in the box of range 1 through n. So all parameters are in the range between 1 through n, then we can count the number of such progressions, or linear progressions. So the heuristics for what you see, so there's a constant, this, I don't know, how do you call this?
Singular series.
Yeah, no, how do you call this letter? Is it S? It would be a, yeah, singular series, I know. So the singular series, there's a constant associated with this collection of polynomials, and the heuristics would be that n to the r plus 1 is the count of the number of variables. So I have r plus 1 variables go up to n, and we think of each one of them as, each one of these expressions as being prime with probability more or less 1 over log n, so that accounts for the 1 over log n to the k. So, and then there's this constant that we can calculate explicitly. So, for example, you can get the number of 4-term arithmetic progressions, and this is a special case. You can calculate this number explicitly. So the result I want to talk about today, or which is the motivation for what I really want to talk about, which is the concatenation of cubic structure, is the following. So what can we say if these polynomials are not linear? Well, what we hope to say is the conjecture there, but we can't quite say that yet. But this is a recent result with Tao, that the conjecture is true if all the degrees of all polynomials are bounded by some number d, and the differences are of degree exactly d. So what does that mean? It means that the degree d of coefficients are all distinct of the polynomials. So if all degrees of pi minus pj are all exactly d, then the conjecture is true. So we have this kind of local to global principle. If we have no local obstructions, then we can have them all prime. And furthermore, we can calculate asymptotics, but only in the largest range possible. So if we take, or more or less, okay, so there's some, I'm going to do some slight cheating along the way to make exposition easier, but more or less something like this. So maybe all the theorems I state, which should be maybe with some quotation mark. but I want the ranges of the parameters to go all the way through. So if the degree is d, then I need, to get asymptotics, I need all the parameters to go all the way to the range of n to the 1 over d. So the monomial, the d degree monomial will be of order n, okay? Right, so for example, we can calculate asymptotics and for the number of expressions, say of the form x plus n squared plus n plus 4, or something like that. Or the second example, this is with two variables, with polynomials with two variables, say x plus nm, x plus nk, x plus nm plus nk. And this second example is the one that's going to be our working example. So I want to explain the strategy through this working example. Okay, working example. So I want to explain first why are polynomial progressions more difficult to understand than than linear ones. Well, okay, we all maybe intuitively understand that, but why? What do we need for our strategies, or what is the problem with the current strategies that we have? So this is even in this case. So the case of x plus nm, x plus nk, x plus nm plus nk. I won't say that anymore because it's too difficult. But suppose we take all, so this is where I want to take the range of all my parameters to go up to square root n. And so x goes up to n, and n, m, and k go up to square root n. And I want, let's try first to compare this to another kind of, or average, or set of polynomials that is much better understood. So suppose I was just looking at x plus u, x plus v, x plus u plus v. So it looks very similar, but now I allow u and v to go all the way, range up to n. And if I try to understand the second expression that I wrote down here, then if I try to count the average number of these expressions for some function, then the second expression is very easily analyzed via Fourier analysis. So if I have some function f taking values in -1, 1, say in z mod nz, on z mod nz, and I try to count these expressions for this function f, then this is controlled if I apply discrete Fourier analysis, then this is controlled by the largest Fourier coefficient of the function f. So I have a good understanding of the function if I understand Fourier analysis, okay, or some understanding of the function against linear exponentials. But if we try the same thing for the former average, for the one with the, I'm not going to say again, is then at least naively, well, if you try to apply just discrete Fourier analysis and try to see if you can work something out, then at least naively you can't do this, or I don't know how to do this. Okay, so before I go to explain how to work our working example, so let's look at a slightly different variant of it. So now suppose I look at this average x plus m, x plus k, x plus m plus k, but I take the variables m and k not all the way up to n, but all the way up to just square root n. Okay, and I want to see what can I say. Well, in this case, I can have some information using kind of local information on the function. So I can make a local shift. So I shift by some variable y of range in the range 1 through square root n, and I fix x, and I look at, and then I have these kind of similar expressions to the ones I had before with all. So I replace n by square root n. So I have this kind of local understanding of my function. So we have control over the sort of local Fourier coefficients at scale square root n. So here's a conjecture, for example, for the behavior of the Möbius function. So the conjecture is that. So maybe I didn't. The Möbius function is a function that is associated to the prime. So it's a function that takes the value 1 or -1, depending on the number of prime factors of the number. So and 0 if there is if the number is not square free. So it's an important function in number theory. And for example, like one conjecture that we have for this function is that if we look at the local Fourier coefficients of this function, so this notation that I use over here, so I think now of this Mobius function, I fix an n, and I look at the interval n through square root n, and then n through n plus square root n, and I think of this as a function over there, and I look at the Fourier coefficients over there, and I take the sum over the supremum of the Fourier coefficients on each one of these local intervals, then we conjecture that you should have cancellation there. Actually, the conjecture should be true. This should be true for reasonable conjecture would follow from Chowla's conjecture that if, for a well-known conjecture in number theory, that if I don't have to take square root n there, I could take any range h there that grows slowly to infinity as slow as I want, then I would still expect this thing to happen. In which case, yes, so I look at I think of this as a function on n plus square root n, and think of it as periodic. Yeah, I'm all cheating around here, so I didn't want to write the exponential function, whatever. Yeah, but I think of it as a periodic function there, and I look at the sort of discrete Fourier analysis in that interval.
It's the sum of Mobius and range
against exponentials. Yeah, exactly. Yeah, so exactly that sum, and maybe I think so this type of information, if we knew this for h for short h, as I said before, then that would, maybe Terry's going to talk about this tomorrow. So this is related to this logarithmic averaged Chowla conjecture. But if we knew this, if we knew this conjecture over here, then we could deal with averages with short ranges, okay, for the Mobius function. For example, if we knew this thing over here from this analysis that I described before, from the fact that the local averages are bounded by the Fourier coefficients, then we would, maximal Fourier coefficient, we could get sort of an estimate for an average of the Mobius function for this expression. Okay? Yeah? Okay. Yeah. All right. So how do we want to think of this average, and what is? So here, back to our working example. So think of this, fix an interval 1 through n, and look at its dilation by a number n1. So look at n1m, fix an n1, and think of it as m through square root n, and n2m for two different numbers, n1 and n2. And we want to think that for many, so for most maybe, or depending on how we want to quantify it, but for many choices of n1 and n2, so I want to think of these k and n as sort of subgroups. They're not exactly subgroup, but I want to think of them as subgroups of the interval 0n and was interval 1n, and they're independent in the sense that for most choices of n1 and n2, if n1 and n2 are not related, then if I add these two subgroups k and h, then I would get something of size n and of bounded multiplicity. So it's something like full range of what I'm looking for. Okay, so how is it that we want to think of, or what is the problem we want to understand when we're looking at these averages? Yeah, bounded multiplicity. So that's what I wanted. That's what I said before. So here's the problem. So we're looking at take these cubes that the cubes that I saw, like the cube x plus k1, x plus k2, x plus k1 plus k2. But I think of this as the cubes along the k direction with the subgroup k. And I have this other cube in the h direction. So I have x plus h1, x plus h2, and x plus h1 plus h2. So these are the two cubes. And think of it as, suppose I have some information regarding the h direction. I have some cubes in the h direction and some information regarding cubes in the k direction. Can I concatenate this information to information about global cubes in the k plus n direction? So which would give me something at global scale, n, which I might have some information about. So here is this is the key question. So can we concatenate cubic information? I'll try to make this more precise later, but I tried to concatenate this cubic information along K and along H to get some information about cubes along K plus H. Okay? Right. So here's some simplified version. So here is, again, the problem. So I have some abelian group G, and I have two subgroups H and K. These are subgroups of G. So that's not the case we had before, because they were not real subgroups. But the techniques are the same. So we have two subgroups of an abelian group, and we're given information on some dimension cubes in dimension A along the H direction, and other information, and some information about cubes of dimension B in the K direction. So before I had two-dimensional cubes. That was, you saw, right? It was a two-dimensional, maybe parallelepiped or a cube. But in general, we can ask this question for any dimension. And we ask, can we say something about can we infer some information about cubes along the K plus H direction? So to just give you an example of what we can hope that will happen, let me introduce some notation. So the first equation there, the delta HF, so we introduce this notion of discrete derivative. So I have a function f, and I can discretely differentiate it. So this is kind of a multiplicative derivative. So look at f of x plus h times f of x bar. And for example, if I maybe that was a bad choice of h and k, considering the h and k there. So think of this as h1 and h2. Would have been better choice of parameters of what I'm trying to explain now. So suppose you look at, so if I differentiate twice, then I get this kind of two-dimensional cubic average. If I differentiate 8 times, then I get something that looks like an 8-dimension expression. And we'll say that f is an h polynomial of degree smaller than m if, when I differentiate along the h direction m times, my function trivializes. Okay? So here's an example. Yes. So say your group is just z squared, and you're looking at the subgroup, which is the 0 times z, and the other one is 0 times z. And suppose you're looking at fixed sum number t, and suppose you're looking at this function f of xy is equal to e to the xyt. Then this function is of degree of, it's linear in the x direction, and it's linear in the y direction. So it's linear in the h direction and linear in the k direction, but it's not linear in the as a function of two variables. It's a quadratic function as a function of two variables, and it's not linear in G, but it's not all is lost. It's of degree, it's of bounded degree, so it's of degree smaller than 3 in G, okay, in the whole group G. Sorry? Yeah, okay. Yeah, well, right, fine. Thanks. Yeah, there's an I there. You should be sleeping. Okay. 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 So here's a simple fact. So suppose H and K, again, the same setting. So H and K are subgroups of a finite abelian group, and so here's a simple fact: if your function is a polynomial of degree. It's an h polynomial of degree smaller than a and a k polynomial of degree smaller than b, then it is an h plus k polynomial in degree a plus b minus 1. So this is very easy to show. So you can take it as an exercise while I'm speaking. Slightly more difficult to show is what you could think of as the 99% question. So suppose you know that your function is a smaller than a degree polynomial in not on all h cubes, but on some almost all h cubes, and you know that it's a 1 minus delta degree polynomial. Oh, sorry. I can't, whatever polynomial for almost all k cubes. then you can ask the question, is your function close to, I'm very happy with that. So is your function close to an h plus k polynomial of degree a plus b minus 1? And indeed, that's true. So you can use arguments that are similar to the arguments of Alon, Kaufman, Krivilevich, Litzin, and Ron to deduce this argument. So to deduce that f is close to an h plus k polynomial of degree a plus b minus 1. And the idea is that if, in this case, when in the 99% world, you can try to hope to guess what your polynomial would be. So you would ask again, your guess would be the same guess as this question. If you, your guess would be at the point x, I want to know what my value should be. Then I ask my h plus k cubic friends what my answer should be. I majority vote on them, and then and this would give me a polynomial of and that is very close to my function and is of the correct degree. So but the question we need to address is, what can we say if we only know this on a small non-trivial portion of the cubes? So suppose I know, so this is the 1% question. So I'm living in the 1% world, so what does that mean? So suppose I know that my function is an h polynomial on only a delta proportion of the cubes, and I know that it's a k, right degrees. Okay, and it satisfies the condition of a polynomial on degree on many and a non-trivial number of cubes with respect to the h direction, and non-trivial number of cubes with respect to the k direction. Can I say that my function in some way satisfies, or is this close to, or in some way, is it in some way related to a function satisfying this condition for an a plus b minus 1 degree cube? And to try to make this question more precise, one can introduce the count for this, or you can introduce the UHA Gowers norm. So H is for the subgroup H, and A is for the degree of the cube you're looking at. So it would be slightly, so again, there is a slight, the definition, the true definition is slightly different to make this thing positive and actually a norm, but it's almost very similar. So what would I do? So I'm looking at these derivatives, and I'm counting all. So to say that this first condition is true, for example, would say that this norm is non-trivial. So it's bounded away from 0. So in all these questions, I think of I have a sequence of n growing, like in Yuval's talk. So you don't think of one fixed n. You think of a series of a sequence of intervals growing, and you want to understand. So these are delta is independent of n. Okay, so I have these norms. So I'm counting all the numbers of the number of times this thing trivializes, and I'm averaging over all possible parameters that I have, and the theorem that we can prove is the following. So suppose I have a bounded function. So I have a function from G to the unit disk, D. And suppose you know that you have some cubic information in the H direction. It's greater than delta. In the K direction, it's greater than delta. Then you have this cubic information with respect to same type of cubic information, but with a bad constant that depends on delta. What? No, we can't. Don't even know how to, not sure what to say even. I haven't thought about that. But no, nothing that is explicit, nothing that would work for anything, would be good for anything that you would want to use it for. Okay? So, it should be, I believe that there should be a good relation there, but I don't, our proof doesn't give any.
With the compactness, there's no quantitative?
Yeah, actually, yeah. So it works in the ultra filter limit, and yeah. Okay, but I do have, there's some good news in it, is that in order to prove this theorem, so it's a much softer theorem. So you can try to ask if you can try to understand these norms, these UHA norms. And so if we look at the, if we're inside Z mod NZ or inside, and we're looking at the H, which is the full H is the full Z mod NZ, then even that is a difficult problem. And we know how to solve it now, but that's what feeds into the first theorem that I described about polynomials that are linear. But in general, it's difficult to understand these norms. And the good news is that in order to prove this concatenation theorem, it's a soft theorem. So you don't need to understand exactly what these norms are. You just need to understand that they come from some averaging procedure. And so what you can do is, instead of trying to understand the specific norms and where they lie, you can work with what we call the dual functions. So what is the dual function? So maybe I should have shown the average again before, but we were averaging, for example, in the case of the degree smaller than 1. So there was this average. There is an f for the full U2H to the form norm. This is just this average that's written over there, this one, and you multiply it by f of x. And if you do that, then this is just this expression that you have over here. So what is good about these? So you forget. So you think of it as an f of x times this average, and the UK norm is the inner product between the two of them. So it's just this FDHF. And the good thing about them is, first of all, about your function f, that it correlates with one of these functions, with these dual functions, with this dual function. And the second thing is that, so that gives you a good feeling that this is what you should work with, and this is that these dual functions, you secretly know that they lie in the right classifying space of these UH norms. So you don't, this tells you sort of that this is a creature you can work with instead of understanding the norm itself, and you can use its kind of averaging properties in order to show something like, so what you need to show is that if you look at the space that is generated by the by the dual functions with respect to the k action and the k cubes, and you look at the space generated with respect to the h cubes, then it lies inside the space that is generated by the cubes with respect to the h plus k direction. Okay? Okay. So here, how can we apply this to our model example? So suppose you have a function f on z mod nz, and suppose you know that your function has u3 norm that is smaller than some epsilon. So for example, for the Mobius function mu, we know that the u3 norm is little o of 1, so it approaches 0 as n approaches infinity. Then what you can infer from the type of argument that I said before, from the fact that if you understand the averages along nm, when n1m, so you fix n1, and you for many choices of n and m, for many cubes of size square, dilated cubes of length square root n, you can many pairs of cubes of direction n and m, you can concatenate to information about a cube of size, many one-dimensional cubes, you can concatenate to information about two-dimensional cubes. So you, or not one-dimensional, one polynomial. So many two-dimensional cubes you can concatenate to 2 plus 2 minus 1, which is 3 dimensional cubes over there. So you can find, so if you know that a function has small u3 norm, then you can conclude from that these averages are going to be small as well. So for example, for the Mobius function itself, you can conclude from this that this average is little o of 1. So if I know that mu is little o, the u3 norm of mu is little o of 1, then I can show that then it follows that this average is little o of 1. And you also see from this why I have to take the parameters ranging up to their maximal value. Because the information I have about the only thing I know about many arithmetic functions, for example, the Mobius function, is information at large scale. and I need, if my information is only when all parameters are of size square root, and you can maybe, in this case, you can actually make it maybe slightly shorter. But if all my information is at scale n, then I need all parameters to go up to square root n in order to get an n-dimensional information about something of scale n. Okay? Okay. So let me say some remarks about this. So one is using, if we are interested in the question about saying z mod nz, and we do understand functions that have small, or we do know we have a classification theorem for the U3 at scale z mod nz norms. So we understand this well. This, as I said, this is what feeds into the this theorem about linear progressions. We can feed this information, this classification, into this back into this average over here, and then find out that actually, in retrospect, this average up here is actually controlled by the U2 norm. This is, which means that actually there should be some way to prove this theorem just using Fourier analysis, because Fourier analysis is just saying the U2 norm is like what is governed by the U2 norm is the two-dimensional cubed, which are governed by Fourier analysis by the largest Fourier coefficient. So there should be some way to prove this using just Fourier analysis, but I've asked, or circle method or whatever, I asked circle method people, and they couldn't come up with a proof for this. So I don't know how to do this without first going to the U3 norm and then coming back down to the U2 norm. So you're first going up to a higher degree and then showing that actually you need something smaller with the information of the classification for the Gowers norms. So that's one thing. A second remark is for applications to the primes, this theorem that I described before is that what the proof is for bounded functions. And if you want to make this work for the primes, which are unfortunately, if you want to work with the primes, then you have to work with a non-bounded function, which is the Fomangold function, which is, it takes the peak log p of the prime p. Then you need some transference machinery. So you want to use the green tau transference machinery, but that actually is not sufficiently, well, at least as doesn't quite work, but then fortunately, I can mention Noga again. Yes, fortunately, there is this simplification of the green tau transference principle by Conlon, Fox, and Zhao. And Zhao is a grandson of Noga, and they allow us to actually push this further to make this transference work in this case as well. And so first you need to transfer this theorem to functions that are not bounded, but actually bounded by what is called a pseudo-random function. And the second thing you need to do is, again, you need to feed in the classification of the global norm. So you need some information. You need the full what is known as the inverse theorem for the Gowers norm to make this work. Yeah, and maybe just one last comment is that actually, well, we would like to make this work if you wanted to make this, if you want something that would work for all polynomials, not only for those satisfying that they have distinct, the differences have distinct degree, degree exactly d, then we would need something like the conjecture I wrote before, but which we don't know how to prove, but we can do some special cases of families of polynomials. For example, x plus n, and x plus n squared. This is something that we can sort of get rid of the highest order. So using the techniques, we can get rid of the x plus n squared and replace it by 1. And x plus n is understood at scale square root n, for example. It's understood at scale n to the 1/6 plus epsilon or something like that. So we could do even x plus n to the 6, or maybe 5. Okay. Okay. So I was very worried that I would run out of time, and before the when everybody wants to hear all the nice stories and family comments about Noga. So I am done. Happy birthday, Noga.